So, what are shape functions? What are shape functions?
Which shape, which described with the degrees of freedom.
Yes. So when we have an object, okay. So let us say we want to find out what are the strength requirement if you want to make a blast furnace. Okay. So you have a company and you have given a job to make a blast furnace. Okay. So what are the things you need to know about blast furnace? You need to know that what capacity of blast furnace the industry wants to make. Okay. So if it is 10 tons, based on that you will do a volume calculation, and then volume is decided. Now you know what materials people are using to make the blast furnace. Everything is okay, no? Now how will you find out what should be the thickness of the plate which you want to use for making the blast furnace? Material is known. Okay. So how thick plate you will take? You will have to take a plate and you will have to bend it, weld it. Okay. You will be welding it. Then you will take a plate and then you will weld it. Then you will take this part, also weld it. Okay. So welding is involved. And so what thickness of plate you will take and how will you decide that? How will you do it? You can't make it. You can't make the full blast furnace and check if this thickness works or not, because that will take 10 years. So what will you do?
Just give me a prototype. How much load should it bear? It's a real blast furnace.
Yeah. How will you do it? How will you calculate how much forces are coming on this side of the plate, on that side of the plate, here?
We know the volume.
We know
the
volume.
shape what we want to make.
Yeah.
And we'll do some mathematical calculation, and we'll test in the sample like how much load it can bear with this force.
Yeah. So what you can do is you can define this problem as an axis symmetric problem, right? And you don't need to model the whole thing. You only need to model this one film which is symmetric along the axis of the blast furnace. Okay. Take some thickness and then you model the piece. So make the piece, make the sketch of it, and then allow, either you do hand calculation or you allow some software or some coding so that this plate behaves like the material will behave, whatever material you have chosen. Okay. So suppose you have chosen mild steel. Okay. So what are you expecting? Obviously there is going to be elastic deformation, right? And mild steel is isotropic, so you need elastic modulus, volume ratio. Done. It might deform plastically or not. You want to make sure that it will not deform plastically. Correct? You don't want your blast furnace to become a barrel furnace after 5 years. So you don't want it to deform plastically. In order to ensure that, you need to know how it deforms. Is it making any sense to you? Yes. Okay, so what do you need? You need yield strength. Also, you need the strain hardening behavior. Okay, so suppose this is the stress strain diagram of the particular type of steel which you are choosing. So you want this behavior from here to there. A very crude way of doing that would be to take only this point and that point and immediately assume something. Okay, that is not conservative. Oh, that is conservative. That is conservative because that is the worst behavior you are taking. So conservatism is good, but over conservatism is not, because you are actually not realizing the full potential of the material. Based on this conservative calculation, you might choose a very thick plate which you don't need, which will unnecessarily cost you a lot of money because you are making the blast furnace. Okay, so you don't really need to make the whole thing, you just need to model it. Okay. Instead of imagining the effect of curvature, because there is an angle there, there is an angle there. Material is deforming elastically, plastically, so you need to update with how much amount of strain is coming because of the forces. Apart from that, you also need to take care of the temperature. There is a temperature, there is a ceramic lining. Okay? This ceramic lining will have some thermal conductivity. So how much temperature is there, how much temperature is here, and then you will assign that boundary condition, that on one side you have that temperature, that side you have that temperature. So thermal strains will come. Okay? Apart from that, you can have creep deformation. Right? Also, how many times you are shutting down blast furnace for repair? Or you don't have customer, you are a very bad company. So only 2 customers are asking for steel every quarter in a year. So for the rest of the 3 quarters, your blast furnace is down, or at least 2 quarters. 1 quarter you're repairing, and then you're going home. Okay. So every year, 1 quarter, it is switched on, and then it is switched off. So then thermal strains are coming, going. So there is a cyclic loading then. Okay. That cyclic loading might cause low cycle fatigue. Okay. So you need to take care of monotonic plastic deformation, elastic deformation, creep deformation, fatigue deformation, thermal strain. And if you shouldn't, but if you are putting your blast furnace in some harsh environment, then corrosion can also happen. All those things, can you do it theoretically? That is very complicated and also open to a lot of errors, because analytical calculation, but people do that. So mathematical modeling of blast furnace is done. For the first time, I believe it was done by Lahiri from IISc Bangalore, and so you can, and in mathematical modeling of blast furnace, you can also do mass balance and force balance, heat balance, all those things you can do. That is a part of modeling any furnace. Okay? So we need to take care of all those phenomena. So what I can do is, I can divide this film. I have simplified this problem by making it axisymmetric. What can go wrong by this assumption of axisymmetry?
The force on this side will not be equal.
Why?
If we test by putting a liquid in there, and so the force the liquid will.
No, it is axisymmetric. Are you saying that there is no force on this side? Are you saying that?
This side,
On this side?
middle boundary.
On the middle boundary, you will have force. Yeah, you can define it. That you can do. So when I model it, I will not put liquid in it. I will say how much hydrostatic stress is coming. That will be my boundary condition. My boundary condition will be how much temperature is on the surface. I'm not bothered how much temperature is here, because that is not going to the plate. Okay? So when I assume this to be axisymmetric, what might I miss? There could be many things, but one thing which I might miss is that whenever I make a plate, I cannot be sure that the thickness is uniform all along. And that is a complicated thing to take care of. Okay? So that variation I have to deal with. And how do I deal with that? Factor of safety. Okay? So I have this piece now, which I want to understand under the boundary conditions that I have hydrostatic stresses and temperature on this. So then I divide this into pieces, small pieces. Very, very small pieces. And in all those small pieces, I take things, so I assume that these small pieces are so small that all the variations are linear. Okay? So I take one box, and in this box, what do I need to vary? I need to vary displacement from this to that, this to that. Also temperature in all the directions. Okay? So U and T are my variables. Okay? Which I am trying to calculate also, interpolate also. And if I assume the variation of this degree of freedom from this point to that point linear, then that is my linear shape function. Okay? So I say that displacement from whatever value is here and there, U2, U1 and U2. Okay? So the displacement anywhere between U1 and U2, I can describe it as this. So I can simply write, in this case I will be writing N1 U1 plus N2 U2. If I have more number of elements, more number of nodes, nodal values, then it will go on. So Ni Ui is implicit that you have to sum over all the values of indices. Okay? Right? I can also make it quadratic or any other polynomial, and so that's why the name shape function. It can be linear, it can be quadratic. Usually linear and quadratic shape functions are used in commercial finite element analysis softwares. Okay? So we will also be using these two in the lab part. If I divide this plate into 100 small boxes like that, and if I divide this into 10,000 small boxes, will it make a difference?
Yes.
Why?
That's why we're dividing.
What?
More than
That's why. What? That's why I'm dividing. No, I'm asking an open question. If I divide,
डिवाइड करने से फर्क नहीं पड़ रहा तो तुम
अरे ये लॉजिक कहाँ से आ रहा है भाई? कि डिवाइड करने से फर्क पड़ रहा है इसलिए डिवाइड कर रहे हैं. हाँ? It is like why I'm digging a hole. Because you are digging, you will get water.
So because we are considering that variation is linear, but not necessary that it will be linear.
Yes, yes. Very good. So along this point to that point, if suppose, so let us take this point and this point, and I only have two elements here. Okay? And my shape functions are linear, so I am going to get something like that, and then there is a slope of change in slope. So I'll get this kind of variation, which is what you are doing in that cantilever problem. Right? So you can see, and that's your assignment, if you divide it into more number of pieces, the values which you are calculating from each element will come very closer to the analytical solution. And why? Because there is a gradient which less number of elements will not be able to capture. Okay? So suppose that, again from this point and that point, the real variation of displacement is something like this. Okay? And you have divided into, let us say, four elements. Okay? So here you probably get one point which is there, and then you get another point which is here, and then in this element you get a displacement value which is somewhere there and there and there and there and there and there, something like this you get. Okay? So your calculated profile of displacement will be like this. Right? You don't have any value between these 2 points. If you further divide it in more pieces, so instead of 4 you have 8 now, so you will have 1 point here, 1 point there, more, 1 extra point there, 1 extra point there. Okay, so if the curve was really like this, and because you only had 2 points, 2 point के बीच में straight line ही draw हो सकता है. Okay, so if you have another point, because now you have one more element there, you can get a profile bilinear. More elements, it will become a polynomial, isn't it? Right? Another way of doing the same thing is that not to divide one element into 2 pieces, but one element, but a shape function which is quadratic, not linear, or cubic, or polynomial. Right? Instead of dividing into 10 pieces, I can have a 10-degree polynomial. Right? And I can achieve the same thing. So both of these two methods are causing the same result, gain in accuracy. Right? So which one will you prefer?
Higher number
Hmm?
samples.
So when we divide elements, more number of elements to increase accuracy, that is called H refinement. Okay? And when we use higher order shape functions, then those are called P refinement, because polynomial degree is giving a higher degree. Okay? And why H? Polynomial, so P refinement. H because there is a height. Okay? So which one you will prefer, H or P? H, why?
So because of polynomial, we do not know if it's which equation we need to take.
Yeah, you take any
quadratic, cubic. So
In linear, you are taking linear, no? So if you are using H refinement, that means you are taking linear shape function. So using equation linear, you use a quadratic equation. In any case, you don't know what is the real behavior. If you know, then there is no point in doing it. So you don't know, so you are approximating. Okay? When you approximate a curve, then so here you know that it is linear. Now suppose you want to know what is the real behavior of material. Okay? So you will have an expectation, then you will do, so you will have a prediction, you will go to certain value. Then you will have a corrector which will tell no, you have gone very high. Okay? So then your next fluctuation will be a little lower. Might be a little lower. It's like finding a root. Bisection method or Newton-Raphson method, yeah?
In P refinement, like if we keep on increasing the degree of the polynomial,
Yeah.
it is not important that the accuracy will increase only. It will
That is
be
also not guarantees in H refinement. That point I forgot to make. So now I divide 4 elements into 8 elements. Then I divide into 60 elements. And after a certain point of time, I don't really will have any gain in accuracy, because I'm done. And when I'm refining further and further, I'm just increasing the load of the computer. That's it. That's what I'm doing. Agar real behavior cubic hai, so there is no point in going higher than 3 elements. If I take 10 elements, I will not gain any accuracy. So that same thing will be reflected in H refinement, what you are saying in P refinement also. So hold this question with you and try to answer it before mid-sem. Okay? Good. So the physical understanding of shape function is that, and we also, did we try to derive the shape function or not? Okay, so one method of deriving shape function is called Lagrangian method. Okay, and that method is very simple. So if suppose you have n number of nodes, and but before that I was explaining something in the last class, which was that when we divide this blast furnace or cylinder or trapezoidal, cantilever beam, table, whatever. Not necessarily because of the geometry. So blast furnace is making an angle like this. Okay? You can have a very fine curvature in some objects. Maybe you are modeling a ring. Okay? So every time it is not possible to put all the squares and fill all the space. You might have some space which is left, right? क्योंकि एक गोल कमरे में स्क्वायर टाइल्स बिछाएंगे तो कॉर्नर में कुछ तो बच ही जाएगा ना, right? So in the corners, maybe you need to make an element which is like this. So what am I trying to say is, it may not be a square, it can be a trapezoid, right? It can also be a rectangle, it can be a trapezoid. Not necessarily it has to be a square, right? So every time we will have to take care of this thing, that whether it is a square or not, right? In order to do that, this thing is broken into two pieces in conventional finite element method, and that is to define a local coordinate system. Okay, so global coordinate system is x, y and z, and those values are telling you the real physical position of the material points. Okay, so if suppose you are modeling this and you have kept your origin here and the distance of the first interface of the blast furnace is 10 millimeter, and then you have a thickness of, let us say, 200 millimeter. Okay, so you have done that. So the point of this will be just 10 comma 0, right? If this is the origin, this is the x-axis. So those values are telling you the real location of the material point, right? And then when I define a local coordinate system, this local coordinate system will operate same for every element but inside the element. Okay, whenever you need to connect this thing to the adjacent element, you need the information of real space. So you need the real coordinate system and a connection of local to global, that you need. Okay, so local coordinate system, I define x-axis, I can't call it x-axis, so I call it something else. Okay, so this thing is zeta, but I will call it eta because I always make a mistake in not zeta. I will call it epsilon because it looks like epsilon. Okay, and then y-axis I will define as eta. Okay, so epsilon and eta are local x and y. For each element in 2 dimension, I have one epsilon, one eta. When we will talk about 3 dimension, then we will have a brick element. Okay, and in that I will need another axis, which we will talk when we talk about 3-dimensional elements, and we will do that very soon. Okay, so now we should be happy that we are dealing with 2-dimensional elements only. So now we need a method to find out the shape functions at these nodes. Okay, so very simple. I can define the local coordinate system first. I'll do that. Okay, so the property of local coordinate system is always that the origin is at the center, and whatever is the dimension of this 2D element, whatever is the dimension, it doesn't matter. It will always have a value of +1 on this boundary and -1 on that boundary. It doesn't matter if this dimension is equal to that or not. It doesn't matter. That's the property, that's what we are going to do. Okay? Is it okay? So even if this really is 2 millimeter and this is 1 millimeter, my epsilon value will be +1 here, -1 there, and eta value will be plus 1 here and minus 1 there. So it is shrinking whatever geometry of the real element is to a square. Okay, fine. So now that is done, and now we need to find out the shape functions at nodes, which will be n1 and n2. If I have 4 nodes, then I will have n1, n2, n3, n4. Okay, and any point within this element, I want to know what is the displacement here. So how will I compute that? How will I find out the value of displacement at this point? At A? By using that formula, isoparametric formulation. Okay? So I will say here U is equal to N1 U1 plus N2 U2 plus N3 U3 plus N4 and U4. Okay? So because it is 2-dimension, U is U1 and U2, one in x direction, one in y direction. That will be equal to and then I will have here displacement, which will be U1, U2, U3 and U4. Right? What am I missing? So instead of U, because there is too much confusion, because U2 here I have written as the displacement in y direction, and here U2 is the displacement on node number 2. Okay, so there is that mistake. So let me write it U1 V1 U2 V2, where V resembles the displacement in y direction. Okay, so now on every node I have, so on this node I have U1 and I have V1. Okay, so I have U1 V1, U2 V2, U3 V3, U4 V4. Okay, so what should I multiply this? What should I keep here so that I get that? So U1 will be equal to that. What should I do? Or UX? I should write UX. Yeah? So should I write N1? Yeah? 0, N2, 0, N3, 0, N4, 0? Is it not making any sense to you? No? Row column multiplication?
Yes.
Oh, समझ गया ना? Thank God. So you multiply this with that and you get that. Right? So this is the matrix type of formulation for doing the same thing. Okay. So local coordinate system, how do we, what are the properties of this, and how do we calculate displacement at any location inside is dependent on that. Now we need to define N1 and N2. Otherwise, N1 and N2 obviously you must have fathomed for now that they cannot be constants. If they are constants, then you will always get one value. Okay, so then there is no meaning of that, because at any point you will always have this formula. So obviously ni's are not constants, they are a function, they are shape functions. Okay, so the way we derive it is that, so ni should be L epsilon I into L eta I. Okay, understood? No, I'm going to tell you what L epsilon I and L eta I's are. Okay, so simple trick to what happened?
Sir, these U1, V1, V2 up to V4, these, and on the right side, these are the displacements of each node.
Yes, these are nodal values. Yes.
And sir, what is this then?
This is at any point you have U1, V1, U2, V2, no?
Okay.
At any point in the material, in the element. वही तो concept है shape function का, that you want to interpolate the values. You have the nodal values, and then from those nodal values you want to find out what are the values inside the element. Okay. So you should also understand that at any point within the element, the values are coming from the nodal values. So whatever accuracy you have in nodal values, it cannot increase from that. You are getting the info within the element from those values only. Okay? Okay. So how do we find out now L epsilon I and L eta I? L because Lagrangian. Okay? So the trick is I have to define L eta I, and that will be some numerator divided by denominator. Okay? So the numerator will be any variable in the epsilon direction. Okay? So epsilon, so that's a variable, epsilon, minus all those points, the value of epsilon of all those nodes which are connected in that line. Okay? So if I have, so in this line I have one node and two nodes. Two nodes are there. So I should write epsilon minus epsilon 1 into epsilon minus epsilon 2. Except the point where I am calculating, I have to remove that. If I am calculating at n1, then I will have to remove this one. Okay? In denominator, I will not use any variable. I will use the value. Okay? So that will be what? So how many nodes I have? So I cannot write obviously epsilon 1 minus epsilon 1. The denominator is simply the numerator with the value of the nodal placed in it. So if I would have written epsilon minus epsilon 1 into epsilon minus epsilon 2, denominator will simply be, because I am calculating it at n1, what is the value of epsilon at n1? Epsilon 1. So I will write epsilon 1 minus epsilon 1, epsilon 2 minus epsilon. ये क्या हो रहा है? Epsilon 1 minus epsilon. तो इसका तो कोई पॉइंट नहीं बनता है और उसका भी कोई पॉइंट नहीं बनता है, तो ये दोनों हटा देते हैं. Okay? So when epsilon is equal to epsilon k, and that k is any node wherever you are calculating, those things you have to exclude. Understood? Done हो गया? Clear हो गया? Now same concept with eta. Same thing. So what should we write? Epsilon eta minus divided by, okay, looks very simple, no? So in eta you have to see in this direction, right, because that's the eta axis. Okay, clear? And then ni will be simply that into that. Okay, so let us do it for n1. So n1, for n1 I will write epsilon minus epsilon 2 is how much? 1. Okay, let me make a clear picture. So this is epsilon axis, this is eta axis. So this point is 1 comma minus 1. This point is 1 comma 1. This point is minus 1 minus 1, and this is minus 1 1. Right? and that is n1, well, n1, n2, and n3 and n4. Small n resembling node numbers, capital N are resembling shape functions. Okay?
इस वाले example में 1 millimeter लिया था ना?
It doesn't matter. It can be 100 millimeter. It will always make it 1. That part maybe you missed. It will shrink any shape to a square of dimension 2. Yeah,
Okay. Yes.
1 to minus 1.
Yes, sir.
Okay? It will always deform the things to a square. Okay? And whatever error is coming, that will be taken care of by the relation of local and global coordinates. Okay, so shape function will have a particular relation with the real coordinate system, and that is described by a matrix called Jacobian, which we will discuss. Okay, so for now let us calculate the value of n1, and that will be epsilon minus epsilon 1 is how much? N1 is that, no? So epsilon 1 is minus 1, so that will be plus 1. Right? And then divided by epsilon 1 minus epsilon 2. So epsilon 1 is minus 1, minus 1, minus 1, minus 2. So minus 2. And then what about eta? So the first part is just eta minus. And eta 2 is how much? So eta 2 I have to see here. Not there. Eta axis is this. Eta axis is this. Okay. So the second only element apart from that element, sorry, only node apart from that is n4. You understand? So let us correct this and we write n4. Okay. And then here I have n1, so n1 minus n4. Okay. Eta axis के लिए वो exist नहीं करता है. It will exist only when we are here, when epsilon value is there. Okay. So then n1 minus n4 is how much?
Minus 1.
Minus 1. So it will be plus 1 divided by
Plus 2.
1 minus minus 1.
Plus 2.
So 2. Okay. So this becomes what? Minus 1 by 4. 1 plus epsilon into 1 plus eta. Okay. Similarly, you can calculate n2, n3 and n4. Yeah? You can do that, right? So you should do it. Not now, but you note it down and don't always open the notebooks when the class starts. You should also open it when you go back in hostels and do this thing.
सर
Yeah?
वो एप्सिलॉन वाला पहला पार्ट
हाँ.
सर उसमें ईटा 2 एप्सिलॉन 2 की वैल्यू सर 1 है और वहाँ पे माइनस 1 लिया है प्लस 1
एप्सिलॉन 2 की वैल्यू 1 है. हाँ.
हाँ सर उसमें
और एप्सिलॉन 1 की वैल्यू माइनस 1 है.
हाँ
तो माइनस 1 कितना हो गया? माइनस 2.
सर वहाँ पे ऊपर फॉर्मूले में सर एप्सिलॉन माइनस एप्सिलॉन 2
कहाँ पे?
सर
यहाँ पे ना.
हाँ फिर वहाँ
हाँ.
नीचे
अच्छा, तो यहाँ पे एप्सिलॉन,
सर यहाँ माइनस आएगा नीचे फिर
हाँ
यहाँ
माइनस
से।
आएगा. ठीक है, तो ये हो गया माइनस. ओके, थैंक यू.
ऊपर सर ऊपर
तो
n1
वो
जहाँ-
एंड पे वही आएगा ना.
अच्छा ठीक है
ठीक है ना.
Final answer.
ठीक है
Do I need to correct my answer? Okay, well, he's saying that some. इसको भी 1 minus epsilon कर देता है. So epsilon minus 1. Okay. बट इससे तो माइनस कट जाएगा.
अब ठीक है
Plus
अब उससे नीचे
Plus
इससे तो माइनस कट जाएगा. Then it will be this.
अब ठीक है
Okay. अब ठीक है. Thank you very much. इसको पॉइंट दे दो.
मेरे को भी सर
नहीं बताया. ले लो. अब अगले क्लास से आने की जरूरत नहीं. Okay, good. So n1 will be this, and you should be calculating n2, n3, and n4 also like this, and you will see that the values will be only plus minus, and rest of the things will remain same. So it will be 1 by 4, either 1 plus epsilon, 1 minus eta, or 1 plus epsilon 1 plus eta, or 1 minus epsilon 1 minus eta, things like that. So 4 possibilities are there. All those 4 you will get when you calculate N2, N3, N4. You should do it. Okay, ऐसे ही आएगा, ये तो समझ गया मैं. If फिर एग्जाम आता है तुम लोग नहीं करते हो. Okay, so you should do it. Good. So now we know how to calculate shape functions, and with shape functions we can calculate displacements at any point, right? So this we can do. And how do we calculate strain then? Epsilon ij. Remember MM302, it will always be calling you. Epsilon ij. How do we calculate this? जो बोल दिया वो पास हो गया कोर्स में अभी ही. गोल्डन अपॉर्चुनिटी है. बताओ epsilon ij, how will we calculate? What is the formula of epsilon ij?
Del u by del y plus del u del v by del x.
Very close, but you will not pass because it's not completely correct.
So 1 by 2 into.
Yes.
Yes.
ना रुको, पूरा बोलो. रुक जाओ, पूरा बोलो.
1 by 2 into del u by del x plus del j by del xr.
What is J?
Del u j by del xr.
Yeah, fine. I said that in joke. You will not pass. Okay? But you should get some marks for class participation. Okay? And a better marks for other than just participation. नहीं है, अच्छा आंसर दिया है. So this is this, right? इसको पार्टिसिपेशन का मार्क्स तो उसको ज्यादा मार्क्स. Okay? At the end of the day, it will not count to a lot. 5% है. Okay. Now we know how to calculate strain. है ना विपिन, क्या हो गया तुमको? क्यों याद नहीं है सब? याद था. ग्रेड तो छप गया, वो निकाल ले जब भूल जाता तो. Okay. So now we know how to calculate displacement. So how do we calculate strain? Displacement तो पता है? What is UI? UX? And that is that? हाँ ये रहा. UI भी पता चल जाएगा, है ना? UI is equal to N1 V1 plus N2 V2 and blah blah. So now how do we calculate strain from this? Yes. So epsilon we can write as this. So we can write as del n I by del x and the possibilities of all those into ui, because u is NIUI. So when I have to write del u by del x, I can write del n by del x into ui. Right? When I have to write del u by del y, then del n by del y into vi. That I can do, right? So I can make a matrix which looks like del n1 by del x, del n1 by del y, del n1 by del y, del n1 by del x, and this is 0, this is 0, and then repeat it for n2, n3 and n4. Okay, so let me write it for n2 also. So del n2 by del x, del n2 by del y, and del n2 by del y, del n2 by del x, 0, 0. Then you write it for n3 and n4. Should I do that or you can do that? Yeah? That's simply i's and then replace it with 1, 2, 3, 4 if it is a quadratic element, a square element. Okay? and multiply this with our displacement vector u1, v1, u2, v2, u3, v3, u4, v4. Okay? So how many values are we going to get after doing this? How many columns do I have? 8, right? And how many are these? 3. 8 cross 3 into 8 cross 1. So how many values are we going to get at the end of the day? 3 values. 3 values. We'll get 3 values. Epsilon xx, epsilon yy, and epsilon xy. In 2 dimensions, these are the 3 strains you have. Right? And if you see now, what will be the value of epsilon xx? Row column multiplication. So this whole thing into that. Right? So del n1 by del x, u1. Del n2 by del x, u2. तो कहीं भी shear में problem नहीं आ रहा ना? If you remember this formula, epsilon ij when I is equal to j is simply this. Right? We don't have the other variation. When I have a shear stress, then I have 2 parts, and that you will get because you have both of them there. Understood? This matrix is called B matrix. Because of Balwinder, no, just like that. It has a name B matrix. I don't know why. Okay? I don't know why shape functions are named N. Okay, I have really no idea. But this is called B matrix, and in matrix notification, epsilon is simply B into U. U is a column vector and B is a matrix, which looks like that. Now from strain, we should be able to calculate stresses. And how will we do that? How do we calculate stresses from strain? Huh? क्या यंग्स मॉड्यूलस आगे बोलो बस काटो
एक और फॉर्मूला एक दूसरा फॉर्मूला था उसका
बोलो ना क्या है वो फॉर्मूला इस बार पक्का पास बोलो क्या है फॉर्मूला So you will have 2 different types of matrices which describes the relation between stress and strain. So you will have 1 mu, mu 1, 1 minus mu by 2 for plane stress, and for plane strain you will have different type of matrix, and this is called D matrix. Okay, D. So sigma is equal to D into epsilon, so that is equal to D B U. The story will not end there. Okay, with stress and strain in hand, we will have to calculate something which is bigger than this. Okay, and that we will talk about when we reach there. So for now, the class is over, and if you have any doubts, you can. कोई डाउट नहीं, सीधे घर जाना है। बहुत हो गया, आप जाके सो ही जाऊंगा मैं।